atom. The existence of atoms has been proposed since times of early and Greek philosophers around 400 BC who were of the view that the atoms are the fundamental building block of matter. According to them, it we go on dividing the matter, the ultimate smallest particle of atoms which cannot be further subdivided. The word atom has been derived from Greek word atomio meaning uncuttable or non-divisible. The first definite theory about the structure of matter was put forward by John Dalton in 1808 called Dalton's atomic theory. According to this theory, all matters are composed of extremely small structureless hard spherical particles called atoms. However, the discoveries towards the end of 19th and early 20th century showed that atom has a complex structure and is not indivisible. These studies further revealed that atom consists of still smaller particles such as electron, proton and neutron into which it may be divided. These particles are regarded as fundamental particles because constituent of all atoms. Subatomic particle. The electrical nature of matter has been indicated quite earlier in the form of frictional electricity produced by rubbing ebonite or glass rod with silk or fur. In 1830, Michael Faraday showed that a chemical change occurs when electricity is passed through the solution of certain substances called electrolytes. He established a relationship between matter and electricity and suggested that matter is electrical in nature. However, the discovery of electron came as a result of the study of the conduction of electricity to gases known as discharge tube experiments. Discovery of electron study of cathode rays. The electron was discovered by J. Thomson at the end of 19th century during the studies of the passage of electricity through the gases at extremely low pressure. These experiments were known as discharge tube experiments. The experiment in its simplest form consists of a cylindrical hard glass tube about 50 cm long closed at both ends. It is known as discharge tube or Crookes tube. It is fitted with two metallic electrodes. The tube is connected to a side tube through which it can be evacuated to any desired pressure with the help of vacuum pump. The discharge tube is filled with the gas understudy and the two electrodes are connected to a source of high voltage. The pressure of different gases could be adjusted by evacuation. Under ordinary conditions, gases are poor conductor of electricity. However, when a sufficiently high voltage is applied across the electrodes at very low pressure, the gases become conductor and electricity begins to flow in the form of rays. These rays are called cathode rays. The existence of these rays was shown by scientists like Plucker, Crookes, etc. But the main credit goes to J. Thomson. He studied the properties of cathode rays in detail, which led to the discovery of electron. Cathode, anode, vacuum. This was discharge tube experiment. A discharge tube, this was discharge tube and be emission of cathode rays at a high voltage and low pressure. This was emission of cathode rays at a high voltage to low pressure. These rays moved from cathode towards the anode in form of stream of particles. These are moving towards cathode to anode. These rays were named as cathode ray particles. These were known as cathode ray or cathode ray particles because they originate from cathode. The flow of current from cathode to anode was further checked by making a hole in anode. There was hole in anode. And coating the tube behind the anode with fluorescent material. There was a coating of fluorescent material. Zinc sulfide. When these rays after passing through anode strikes the zinc sulfide coating, a bright spot on the coating is developed. Same thing happened in the television set. Properties of cathode rays. From the various experiments carried out by J. J. Thomson and others, the cathode rays had been found to possess the following properties. First, the cathode rays When only electrical field is applied, the electron deviates from their path and hit the cathode ray tube as point A. Similarly, discovery of proton, study of anode rays. The presence of negatively charged particles, charged electron in an atom suggested that there must be some positively charged particles because the atoms of the whole is electrically neutral. In 1836, E. Goldstein discovered that in addition to cathode rays, a new kind of rays are also found streaming behind the cathode in discharge tube experiment. These rays traveled in opposite direction to cathode rays. These rays are also deflected by magnetical and uh, electrical field like cathode rays, but the deflection of anode rays in the opposite direction to that the cathode rays. This means that these rays consist of positively charged particles and were also named positively rays or canal rays or anode rays. Characteristics of anode rays. Some of the characteristics of anode rays are the anode rays travel in a straight line and cast shadow of the object placed in their path. The anode rays are deflected by the magnetical and electrical field like cathode rays, but the deflection of anode ray is in opposite direction to that of the cathode ray. For example, these rays are attracted towards the negatively plate in the electrical field. This means that these rays consist of positively charged particles like cathode rays. These rays also rotate the wheel placed in their path and also have heating effect. The charge to mass ratio of these rays is considerably smaller than electrons. Unlike cathode rays, the charge by mass of positive ratio of positive rays depends upon the nature of gas taken in the tube. The charge and mass of particle constituting anode rays. Unlike cathode rays, the charge to mass ratio of anode rays was found to depend upon the nature of the gas taken in the discharge tube. In case of hydrogen, the charge to mass ratio was maximum. The value was found to be 9.58 into 10 to the power 7 coulomb per kg. Its charge has been found to be 1.60 to 20 to the power minus 19 coulomb, which is equal in magnitude but opposite in sign to that of electron, that is, it has 1 unit of positive charge. Since charge to mass is maximum for hydrogen, the mass of the positive particle obtained from hydrogen is the smallest. Its mass can be calculated from the value of charge and charge upon mass as mass is equals to charge upon mass is equals to 1.67 into 10 to the power minus 27 kg. This mass is about 1837 times the mass of an electron. This lightest positively charged particle was named proton and is also regarded as a fundamental particle. The proton is a subatomic particle which carries 1 unit positive charge 1.60 to 10 to the power minus 19 coulomb and has mass 1.67 into 10 to the power minus 27 kg, equal to that of an atom of hydrogen. Discovery of neutron. After the discovery of electron and proton, a need was felt for the presence of electrically neutral particle as one of the constituents of atoms. The neutral particle called neutron was discovered by Chadwick and it helped to explain the atomic mass of atoms. Chadwick in 1932 bombarded a thin sheet of beryllium element with the alpha particle and observed penetrating rays which consist of stream of neutral particles. The neutral particles were found to have a mass of 1.675 into 10 to the minus 27 kg, which is nearly the same as that of hydrogen atoms and have no charge. These were named neutrons. Thus, a neutron is a subatomic particle having mass 1.675 into 10 to the power minus 27 kg, equal to that of hydrogen atom and carrying no electrical charge. Thus, an atom consists of three fundamental particles: electron, proton, and neutron. Their masses and charge are summarized below in table. Particle electron mass 9.10938 into 10 to the power minus 31, relative mass 5.4858 into 10 to the power minus 4, approximate mass 0, charge minus 1.6022 into 10 to the power minus 19 coulomb, relative charge minus 1. Particle proton mass 1.67262 into 10 to the power minus 27. Relative mass 1.00737. Approximate mass 1. Charge 1.6022 into 10 to the power minus 19 coulomb. Relative charge plus 1. Particle neutron mass 1.67493 into 10 to the power minus 27. Relative mass 7. Approximate mass 1. Charge 0. Relative charge 0. 1 unit charge is equal to 0298 into 10 to the power minus 10 issue or 1.60210. Atomic models. After the discovery of electron and proton, the scientists started thinking of arranging these particles in an atom. Different models were proposed to explain the distribution of subatomic particles in an atom. The first simple model was proposed by J.J. Thomson, known as Thomson's atomic model. Thomson's model of atom. J.J. Thomson proposed that an atom consists of uniform sphere in which positive charge is uniform distributed and electrons are embedded into it in such a way as to give different models were proposed to explain the distribution of subatomic particles in an atom. The first simple model was proposed by J.J. Thomson, known as Thomson's atomic model. Thomson's model of atom. J.J. Thomson proposed that an atom consists of a uniform sphere in which positive charge is uniform distributed. The electrons are embedded into it in such a way to as to give the most stable electrostatic arrangement. The radius of sphere is of order of 10 to the power minus 10 meter, which is equal to the size of the atom. This model was much like pudding, pudding or a cake of the positive charge with a raisins electrons embedded into it. Therefore, the model is also known as raisins pudding model. The model was also compared with Wooden model of positive charge it in which sheets electrons are embedded. Therefore, this model is given different names such as raisins pudding, plum pudding, or watermelon model. Although this model was able to explain the overall neutrality of the atoms, it was soon discarded when Rutherford and his co-workers observed the unusual scattering of alpha particles by the thin metal foils. Rutherford's scattering experiment, Rutherford model of an atom. In other, to understand the arrangement of electron and proton in an atom, Rutherford and his students Hans Gingers and Ernst Masdon in 1909 performed a series of experiments known as Rutherford scattering experiment. In their experiments, they bombarded a target of atoms by subatomic projectile. These projectiles called alpha particle were obtained from a radioactive substance. Alpha particles are high the energy positively charged helium ions having charge plus 2 and mass 4u. They bombard alpha particle embedded from a radioactive substance on a piece of a thin foil or a gold or some other heavy metals. In these experiments, a piece of radioactive substance is placed in a lead block. The block is constructed in such a way with slits that only a narrow beam of alpha particle could escape. The beam of high energy alpha particle was directed at a thin gold foil thickness about 100 nanometer. In order to detect the alpha particle after scattering, a movable circular screen coated with zinc sulfide is placed around the gold foil. When alpha particle strikes the zinc sulfide screen, these produce flashes of light on scintillation which can be detected by examining different portions of the screen. It was possible to determine the proportions of the alpha particle which got deflected through various angles. The following observations were made from these experiments. Most of the alpha particle, nearly 99%, passed through the gold foil unreflected. A small fraction of alpha particle got deflected through small angles. A few are means that mass of the space in the atom particles are positively charged and have a considerable mass. They can be deflected only if they come close to some heavy positively charged mass due to enormous force of repulsion. Repulsion in some particles charged mass present in that atom occupying a very small space within the atom because all were explained to the deflection coefficient heavy positively charged mass. The positively charged heavy mass which occupies only a small volume in an atom is called nucleus. It is supposed to be present. It is supposed to be present in the center of the atom. Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to total volume of atom. It has been calculated that the radius of the atom is about 10 to the power minus 10 meter, while at that of nucleus is 10 to the power minus 15 meter, assuming the atom and the nucleus to be spherical. Volume of nucleus upon volume of atom is equal to 10 to the power minus 15. Fraction of the volume occupied by the nucleus is 10 to the power minus 15. Thus, volume of the nucleus is extremely small in comparison to that of an atom. The difference in size of nucleus and the atoms can be understood by realizing that if a cricket ball represents a nucleus, then the radius of atom would be about 5 km. All these types of deflection of alpha particle from atoms are shown in figure 8. It is clear from the figure that the alpha particle which passes at large distance from the nucleus to suffer any deflection marked alpha. Those which pass close to the nucleus suffer a small deflection marked B, while very few which hits the nucleus are either deflection either deflected to large angle or they retrace their path marked C. C in diagram. A B C. On the basis of the above experiments and observations, Rutherford proposed a model for the structure of the atom called Rutherford's nucleus model of atom. Rutherford's nucleus model of atom. The main feature of this model are in an atom, the mass and the positive charge is concentrated in extremely small region at the center known as nucleus. The volume occupied by collectively known as nucleons. The son of and protons is known as mass number. Mass number is equals to number of proton plus number. Mass number is generally represented by letter A. Therefore, from the knowledge of number and mass number of an element, the number of electrons, protons, and neutrons can be easily predicted. We know atomic number is equal Z is equal to number of protons or number of electron. Mass number is equal to number of proton plus number of neutron. Therefore, for an atom with mass number A and atomic number Z, number of electron is equal to Z, number of proton is equal to Z, number of neutron is equal to A minus Z. For example, lithium has an atomic number Z is equal to 3 and mass number 7. Therefore, number of electron is equal to 3, number of proton is equal to 3 and number of neutron is equal to 7 minus 3 is equal to 4. Generally, Generally, an atom is represented by atomic number is written on the lower side of the symbol and the mass number is written on the upper side. For example, lithium with atomic number is equal to 3 and mass number equal to 7 may be represented as lithium 7 और lithium 3. मास नंबर ऊपर रहेगा A, एटॉमिक नंबर नीचे रहेगा Z और सिंबल ऑफ एलिमेंट बीच में रहेगा जहाँ की X. Isotopes, isobars, and isotones. Atoms of the same element which have the same atomic number but different mass number are called isotopes. Since the atomic number of different isotopes of the same element is same, it means that they have same number of electrons and protons. The difference in their mass number is due to different number of neutrons present in their nuclei. Hydrogen is the common example which has three isotopes. These are commonly known as hydrogen, deuterium and tritium. These three isotopes have the same atomic number, but one but number one but different mass number 1, 2, 3. Atomic number 111, mass number 123, number of electron 111, number of proton 111, and number of neutrons 0112, 012. Hydrogen, deuterium, tritium. Similarly, chlorine has two isotopes having same atomic numbers that is equal to 17, whereas their mass number is 35 and 37. Hoppa, hoppa, hoo. You can see atomic number of chlorine, isotopes of chlorine and carbon, oxygen, nitrogen, sulfur, uranium. It may be noted that the chemical properties of atoms are mainly controlled by electrons, which are determined by the number of protons in nucleus. The number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all the isotopes of the given element will show almost same chemical properties. Isobars, atoms of different elements having the same mass number but different atomic number are called isobars. Since isobars have same mass number, therefore the sum of proton and neutron in the nucleus of each atom is the same. These atoms differ in their atomic number and therefore they have different number of proton or electron and also different number of neutrons. Isobars are atoms of different element and hence they have different properties. Isotones, atoms having same number of neutrons but different mass number are called isotones. Thus isotones have same number of neutrons. These atoms differ in mass number as well as atomic number. For example, silicon 30 by 40 phosphorus 15 proton 16 neutron, silicon 16 proton 16 neutron, isotones because all have 16 neutrons. Similarly, carbon 6 proton 8 neutron, nitrogen 7 proton 8 neutron, oxygen 8 proton 8 neutron are isotone because all have 8 neutrons. Isotopes have same number of protons but different number of neutrons. Isobars have different number of protons as well as neutrons but same sum of proton and neutrons. Atoms have same number of neutron but different number of proton. In all neutral atoms, number of electron is equals to number of proton. Now we solve examples. Like this, we will solve question number 3. Bromine 80 by 35. Third, bromine 80 by 35. Atomic number is equals to Z. Mass number is equals to A. Z is equal to 35. A is equals to 80. Electron is equals to Z is equals to proton is equals to 35. Neutron is equals to A minus Z is equals to 80 minus 35 is equals to 45. Neutron is equals to 45. Neutron is equals to 45. Z is equals to 35. Answer was this and this. So example 1 was completed. Now example 2. Will solve tomorrow.